So distance, speed, and acceleration, they all relate to each other when looked at with time. So when you know the distance traveled in a certain amount of time, you're able to work out the speed that was traveled and also the acceleration that was traveled. Now that I did touch upon this at the beginning of the series or beginning of this unit, but now that we know a bit more about differentiation, I'm going to go into it in slightly more detail and try and give a real life example to show how they all relate to each other. So to start off with, for this example, we're going to call distance position. So we're going to give that the symbol p. So how the position changes over time. So p is a function of time. We know that if you differentiate position or distance, you're able to work out the velocity. So that's really useful. But also, when you differentiate the velocity, you're able to work out acceleration. Now, you're able to work out acceleration. And this is kind of what I was saying in the first slide. We have distance measured in meters, and then we differentiate with respect to time. So you have meters per second. And then you differentiate velocity with respect to time as well, and you have meters per second squared. And you can work out all this information from just knowing the position with time. Now I'm going to do a real life example to try and give you a clear example of what's going on. So in this example, the displacement in meters of a rocket taking off in a straight line is given by p equals 10t cubed add 5t add 4, where time is measured in seconds. So we need to work out what the velocity is at 2 seconds, and then what the acceleration is at 2 seconds. So how are we going to work this out? Well, if this is an equation for the displacement, that will give us the position. So we'll be able to work out the position. And we know from before that the derivative of position is velocity. So what we need to do is differentiate this expression and then put in our time for 2 seconds. So let's just go ahead and do that. So you have p equal to 10t cubed plus 5t plus 4. So that's p t. Oh, that's very good. And then, so what is p dash t, which is also equal to velocity v of t? That is equal to 3 times 10, 30t minus 1 squared plus 5t. So that t just becomes 1, so that just becomes 5. So that's our expression there. So now we want to sub in for the time at 2 seconds. So v at 2 seconds is equal to 30 times 2 squared plus 5. So that equals 30 times 4, which is same as 60 times 2. So that's 120 plus 5. So that is equal to 125 meters per second. That is the velocity after 2 seconds. So what about now? Now that we have the velocity, how do we work out the acceleration after 2 seconds? Well, we already have a formula for velocity here. V equals 30t squared plus 5. And we know that v dash t is equal to a of t. So we can just work this out. So here we have 30 times 2 times 2t to the power of 1 plus 0, which is just the same as 60t. Then we can just sub in our value at 2 seconds. So we can go a of 2 is equal to 60 times 2, which is equal to 120. So and it's this acceleration, so it's meters per second squared. So there we have it. We have an expression. We have an answer. We have an expression for the velocity. We also have an expression for the acceleration. And then we've also evaluated them both after 2 seconds. So you can see now, hopefully you can see clearly now how position, velocity, and acceleration all relate to each other, and how you can use just when you just have information about the position or the distance, and use that information to figure out velocity and acceleration. So I just really want to hammer home this point about the derivative. I've written here, it quantifies the instantaneous rate of change. Just the rate of change at that exact precise second. So again, you think back to your guy on the motorbike. He's going along, he looks down at his speedometer, and it says 60 miles per hour. What is that telling him? That is telling him the rate at which his distance is changing at that exact moment. If you've got here with distance and time, your graph, your movement might look a bit like that. So so if I want to know how fast I've gone after t seconds, I'm going at t seconds even. I go here, right? And then the slope of this line, the slope of, I'm sorry, I've got the wee thing hidden there. The slope of this line here, that's going to show you, that's going to be your 60 miles an hour. That is the rate of change. So I really want to just make sure that this is as clear as I can make it. So what we're doing with differentiating, we're taking some kind of physical property, and then comparing it to something else, and that gives us more information about the situation. We've got our distance traveled and our time, and by differentiating it, we now know our speed.